torsion, because torsion is also a challenging topic, but I'm sure that we can do it together. So the last problem, the one I just made it up, or and we said this is about 80 feet here. From the center of the wall or the back of the wall is not a big deal. Normally we ignore the wall thickness. So, and we said that from here to here, so don't worry about the thickness of the wall. And "45 feet, and this is 35 feet. And the force that coming, if this is the north arrow, and here it is, the lateral force that's coming from the east-west direction. I give this number here to be 200 PLF. Okay, and these are the walls. Normally we make it solid or hatch it like this. So we said that in the direction of the analysis, the east-west, let me give it the other dimension. I gave it 50, just to make sure I did not forget any dimension. 50 feet. So I said that we do have a total force, assuming this is a flexible diaphragm. And again, this is a flexible diaphragm. I should mention that. So the total force F here is equal what? Is equal 200 times 50. So this will give you 10,000 pounds. Since this is a flexible diaphragm, so F over 2 will come here, and F over 2 will come here. Each side will take half. So here along this side here, this here, do we have a drag force in this direction? No. So drag force is equal 0. Equal 0 for this one here. Because a wall, we have a continuous wall supporting the diaphragm, so there is no any gap. So the transfer will be direct transfer between the diaphragm and the shear wall. But here along this side here, I will say a drag force exists. As I told you, there are more than one way to calculate the drag force. Diagrams, equations, statics, by the way. And these discussed are in the book by Dr. Breyer's book, the one I showed you last time, the timber design book. I prefer diagrams, but I will show you the equation very quick. It's very, very simple. Okay, but if you understand the diagram concept, the one I wrote here, the one I wrote last time, here it is. This is a diagram concept. The tau along the diaphragm, the tau along the shear wall, and after that the net diagram. There is something called net diagram. We wrote together last time. And from the net diagram, I can get the drag force diagram. We drew this last time together. Okay, we can do the same thing one more time. Okay, so along this side here, okay, can you tell me what is the tau diaphragm, which is along the south? Tau diaphragm. Tau diaphragm exists over the entire diaphragm, including the opening, because the diaphragm exists over the opening. Okay, so this is tau diaphragm, which is equal F over 2, which is equation 9-3, by the way, over 80. What is F over 2? F over 2 is 5,000 pounds. From here, the total force is 10. So 5,000 will come this way, 5,000 will come this way. So tau diaphragm is equal what? 5,000 divided by 80. This will give us 62.5 BLF. So this here is 62.5 BLF. So far, so good? Okay. We do have a tau wall. And after you do this a couple of times, you don't have to use a straight edge but I'm trying to use a straight edge to make my diagram a little bit readable to you. Obviously, we have no wall here. So tau wall is equal F over 2 divided by L sum W. And this equation 9-4. Okay, which is 5,000 pounds divided by what? What is the length of this wall? It's 45 feet only. Here it is. The wall exists only over 45 feet. So tau wall is equal what? The 5,000. Enter 45 divided. So it is 111.11 PLF. Next is called the net diagram. Net diagram. What is the net diagram? Is the difference between these two. I have 62.5 coming from the diaphragm, and I have 111 going up. So the difference between them is what? The difference between them is what? Is this net diagram here, this is 111.11 minus 62.5. This will give me 48.61, if my math is correct. Everybody got 48.61. Use your calculator. Always to be with me. At least two things that I get benefit from the calculator while you are here. Can catch my mistakes. Number one. Number two, you get to use the calculator. So this is called the net diagram here along this side. And along this side, I'm still getting 62.5. From the diaphragm. This dimension here is 62.5 because it's still coming from the diaphragm because there is nothing here. This is an opening from here to here, which is a 35 feet opening. And as I told you, the way we check our work is to calculate the area. If you call this is A1 and this is A2, what is the area? Area is the height times distance, which is equal 62.5 times 35 feet, will give us a number. And area 1, which is this area here, is 48.6, which is 6.1, which is the difference between 111 and 62.5 times 45. If these two areas come the same, that means that we did it right. They should be equal. So 62.5 enter, 35 times, obviously with 2187.5, and this 48.61 enter, 45 times, about, with the rounding, 2187.5. Do you see the analogy between this and this? They should be equal. This area here, if you consider this is a positive area above, and this area here, which is below, area 2, I call it area 2, the blue one, they should be equal. Otherwise, we did something wrong. And this will tell us what this is. So what is the maximum drag force? The maximum drag force, this one here, 2187.5. If they ask you which one, what the maximum drag force is, and give you answer A or most nearly B and C and D, okay, maybe 5,000 pound, okay, 0.5 maybe, or 4,000 pound, 0.5, or maybe 3,000, 0.5, or maybe 2187.5. It will give you 4 answers. My answer will be D. And the drag force diagram is like this. Here it is. Can you draw it? Because he might give you a drag force. He give you 4 diagrams and tell you which one is the correct one. And as I mentioned last time, at the beginning of the wall and at the end of the wall, or at the beginning of both ends, the drag force is 0. This is 0 and this is 0. And positive or negative is not a big deal. You can draw it on either side. So this one here, I draw it probably on the upper side. I drew that this way last time. Here it is. And come back to 0. And this is a drag force diagram. And as I told you, this number here is the 2187. I hope 2187.5. I gave you the answer last time. I told you verify this for me, and here it is. This is called the drag force diagram. The drag force diagram. Obviously, time is the biggest enemy for us during the exam. Okay. But basically, you can do the following. You don't have to do all this, but we do it here because we need to understand the concept. And after understanding the concept, you can use any approach or any method. But you can say, wait a second. This opening here, which this is the opening, the 35 feet. The diaphragm exists over this opening. Diaphragm is the roof. The roof must be open. That must exist over the door. Is this correct? So the diaphragm exists over this opening. The diaphragm has shear. Every 1 linear foot is 62.5. Who is going to take this shear? We have a collector here. It's called collector. Remember, it's called collector. Two big, it's called the upper plate or the double plate. They collect the shear from the diaphragm and give it to the wall. This was a bit. You have two pieces of wood on the top over the opening to take the shear from the diaphragm, deliver it to the wall. It's called collector. So every 1 foot they take 62.5. So I have 35 feet. If you multiply 35 feet times this, will give you this number. Because this is the drag force will be increasing from every 1 linear foot is I'm collecting 62.5, 62.5, 62.5, all the way up to here until I reach the end of the opening, which is 35. How much did I collect over 35? So 35 times 62.5 will give us the maximum drag force, and this is what we got. I hope this is very clear, and I hope this is